Hey everyone, I'm Quinn Hubbarth, and today Ryan Redler and I are going to talk to you guys about this semester's qualitative analysis project for the Watson and the Watt Creative Inquiry. This is the team that worked with us throughout the entire semester: Dr. Hudson Smith, Dr. Carl Arrett, Dr. Matthew Boyer, and Dr. Ryan Visser. We just wanted to give a quick thanks to these guys for being so helpful throughout the semester with putting our team together and helping us with code and everything. The objective of qualitative analysis is to help researchers understand many different types of non-numerical data. Whether it be through collection of text, surveys, interviews, or other observations, qualitative analysis can help researchers understand lots of different things. Although qualitative research and qualitative analysis is really useful, traditional methods of qualitative research can be challenging for many different reasons. Firstly, qualitative analysis can be very time consuming for researchers because labeling qualitative data is much harder than labeling quantitative data. Without numbers to represent data, pieces of text often need to be labeled by hand, which is a really time intensive task. Because most qualitative data is labeled by people, also a lot of qualitative data is going to have biases, which can sometimes make it really difficult to use or analyze that data. Lastly, it's often hard to find underlying themes in qualitative data, which is partially due to the labor intensive nature of labeling qualitative data. All of these challenges make qualitative analysis really, really difficult. So, how can AI and machine learning help researchers perform qualitative analysis? Our project's goal is to improve traditional methods of qualitative analysis by using machine learning and artificial intelligence. AI and ML can improve qualitative analysis significantly by speeding up processes, reducing biases, and finding complex patterns in data that researchers might not be able to find. Previously, our team has worked on methods involving semi-supervised learning with text document clustering, as well as data visualizations to help researchers perform this qualitative analysis. However, these methods often failed in helping researchers learn about the data, so we tried focusing our energy on something new this semester.
I'd like to thank Quinn for covering our previous segment, which will allow us to transition into how we're going to attempt to solve these problems. So what we're trying to achieve during this creative inquiry this semester is to firstly help reduce the amount of brute work for researchers. So we don't want them droning over thousands of different samples, and we'd like them to reduce the amount that they have to do to accurately create a model that is efficient. Researchers also don't have to know the labels going in. We don't want the researchers to have to know a priori what the groupings of a data set are going to be beforehand, and we'd like a way of comparing samples instead to uncover those latent groups, which will allow us to have more subtle and specific topics from a data set that are more human-centered and conceptual. So how we're going to try to implement those goals is through a relatively obscure method of active learning called triplet constrained representation learning. So what active learning is it's a fancy machine learning term that pretty much encompasses the pink box in the diagram to the right. It is essentially a feedback loop that is based upon maximally reducing model uncertainty by some measure that the researchers can set. And we pretty much test whether or not we test how certain the model is at the end of the loop, and if it's not as certain as we'd like in its correct answers, we can send it back to the beginning of the loop to again get queried and then labeled by the researchers, trained, and then tested again. So this query is going to be implementing something called using our triplets, as in triplet constrained. We're going to couple 3 random samples from the data set and ask a simple question during the labeling phase whether or not A is more similar to B than C. Meaning that instead of having to know what the groupings of A, B, and C are, we can instead just differentiate them on a conceptual level, how the researchers deem fit, which will allow us to have a much more human-centered groupings emerge from the data set. So our progression in relation to that method is we've tested it on a popular data set called MNIST, which is a collection of handwritten digits that you can see on the left here. So the first question is, why not text data? Qualitative analysis is mainly focused upon textualized data, but we want to make sure that the proof of concept is there and that we're not trying a much harder task before even learning if the method itself is working properly. So we're going to be implementing this these meta criterias upon the digital digits. So instead of having a real feedback loop like we would have in a production level software, where the feedback would actually be given from humans, we're going to have programmable meta criteria like the one in the bottom right called primacy, which is pretty much checking whether or not A is prime, B is prime, and C is not prime, or vice versa. We're going to be using a convolutional neural network to scan in the digits and be able to train the model upon it. So the results are pretty much differentiated by the types of metacriteria that we use, and the accuracy rates that we've gotten from training runs of the MNIST dataset is pretty similar to other traditional methods that have been praised in the past. So as you can see, these are the visualized results, which this is the metacriteria for primacy between all the digits, and this is the metacriteria for closeness between all the digits, meaning that A is closer to B than C. And the primacy is what I mentioned earlier. And you can see how these groupings differ quite substantially, with primacy forming two different main groups, maybe three if you consider orange a third, and closeness actually separates them into 10 different ones, which is a good way of showing how the different metacriteria that the researchers can place in the feedback loop can greatly influence the groupings that can occur in the same data set.
There's a lot of next steps that we can take that we felt were justified by the results of the MNIST tests. Although the MNIST test had a lot of positive results, we noticed that it required quite a lot of training samples to train the model, which meant we needed to make improvements before we could use researcher feedback to train the model. Some ideas for improvements we had were using a variational autoencoder, or a VAE, to pre-train the encoder, pre-training the distance function as well as the encoder, and using active learning. All of these should be able to help us reduce the number of samples to train the model. If all of these things are successful, we can then go on to incorporating researcher feedback and using text-based data. We hope that all of these improvements can make it possible for our researchers to collect meaningful information from qualitative analysis using machine learning. Lastly, to wrap this presentation up, we just wanted to say thank you to everyone who watched our video. We hope you learned something about qualitative analysis and what we did this semester to try to improve our methods.